All right. So we left off last week talking about the valence bond theory, and particularly the localized electron model and what its shortcomings are. It's very useful for to answer a great many questions, but it comes up short with some of its assumptions, where it proposes that electrons are localized. That is, they belong to each of the atoms. And the best we can hope from that proposition is that electrons will share when a bond will be advantageous. And when I say that, I mean lower energy results. But in order to fix that localized concept of the electron for each atom presents some problems. When we draw the Lewis dot structures for many of the structures we've seen so far, you can have 2, 3, or 4 valid dot structures where the atoms each have exactly the same or the same spread of formal charges, which means you can't decide which one's better. So the solution to that, or the fix to that problem, was resonance. We just say they resonate among all of those structures. It doesn't work very well for free radicals, where you have an unpaired electron. Paired electrons are ideal for localized electron model, and free radicals, we just have to sort of bite our lip and accept the deficiency. Localized electron model, the valence bond theory, says almost nothing about bond energies. It can qualitatively compare bond energies, but it can't say anything quantitatively about them. In other words, you can't calculate numbers for bond energies using this theory. Okay, so now we're going to get to, historically speaking, what's coming up is the more recent and the accepted theory for how bonding actually works. This is called the molecular orbital model. And there's the molecular orbital theory precedes that, and then the model is a representation of what's happening when bonds form and molecules form. And we're still talking about the covalent bonds. Ionic bonds are pretty well understood. Covalent bonds require this refinement. Okay, so when we are presented with a real compound that we know is bound covalently, we consider the molecule as a collection of nuclei, and the electrons are shared over the entire molecule. Not just for the bonds, but for the entire molecule, we consider all the electrons shared. It's kind of like molecular communism, right? The electrons are owned by everybody. And the orbitals that we're going to define for this model, because electrons don't exist in some ethereal world. They always have to occupy orbitals. So we've got to define a new set of orbitals that will be a place for these electrons to live. But these orbitals extend over the entire molecule. And again, this Bohr model of the planetary orbital, where Bohr started off thinking that electrons traveled in circular orbits around the nucleus, that's a thing of the past, but it still haunts us. We call them orbitals, but they're not really orbiting. They're sort of, this term is grandfathered in. So it's important for us to recognize that it's simply terminology, it's not reality. Okay, let's make a comparison between the localized electron model and the molecular orbital model. Okay, we still have this concept of orbitals, a place for electrons to live. Localized electron model relies on the atomic orbital as the location for electrons, and we only get bonds when those orbitals overlap and we share electrons. Whereas with the molecular orbital model, that concept is out the window, and we create a whole new set of molecular orbitals to span the entire molecule. So for small molecules, that may be easier to grasp, and that's about as far as we're going to take it for actually presenting the orbitals for molecules. But the concept can and does extend over molecules that are huge. Polymers, for instance. In our bodies, we would have proteins, nucleic acids. These are monster molecules. So you can imagine the calculations required to generate enough orbitals and places for all those electrons is a massive task. And I can't imagine doing it by hand. I mean, and I think that's part of the reason that it came later, because the calculations involved are best done in a computer. Have some competent chemist, and with the cooperation and input from programmers, to create a computer program that will handle the data and generate the models, the orbitals for the model. We're still speaking quantum mechanically, as whether it's atomic orbitals or molecular orbital models. The mathematics is quantum mechanics for both of them. And just to hammer this one even harder, or beat the dead horse, the localized electron model says that electrons belong to atoms, and they're only shared between two atoms as a space between the atoms for the bonds for the orbitals to overlap and the electrons to be shared. Whereas electrons in a molecular orbital model are delocalized. That is, they're spread over the entire molecule. And that concept of delocalization should stick in your mind, as the more delocalized electrons are, the more stable the molecule is. I'm not sure. Let me see if I'm going to get to that so I don't steal my own thunder. Yeah, toward the end of this presentation, we're going to look at some examples of delocalization. In fact, we're going to hybridize the localized electron model and the molecular orbital model to understand some molecules. You still have 2 electrons per orbital, whether it's the orbitals for the localized electron model or the molecular orbital model. It's still 2 electrons per orbital. That's it. Okay. And the energies are quantized. In other words, this chi-squared wave function tells you the probability of finding an electron at a given energy level in some space around an atom, we have the same implication for the chi-square that comes out of the molecular orbital formulas, the quantum mechanical set of math formulas, that the wave function that is identified as the chi-square term also gives you an estimate of the probability of finding an electron at a given energy level and the space that it occupies. These equations, whether they're localized electron model or molecular orbital, have to be solved for quantized energies. And we're still interested in the energy more than we are the location. We're going to give a probability to where you find electrons, but we're really more interested in the energies. Right. Now, we can identify energies for individual atoms. The problem with the localized electron model and molecules is that determining the actual values for those energies kind of breaks down when you try to build a molecule out of it. Okay. So the molecular orbitals are going to be derived from atomic orbitals. So we know the atomic orbitals for say, so let's keep it really simple, say a diatomic molecule. We have so many atomic orbitals for this atom and so many for this atom. And when they combine, if you have, say, 4 atomic orbitals from this one and 4 from this one, you're going to have 8 molecular orbitals that come out of that mix. So the number of orbitals is conserved. And the way we do that is we identify 2 different types of orbital. One is called bonding and one's called anti-bonding. And the terminology there was not chosen randomly. The bonding orbitals are at lower energy, so they're more stable. And the anti-bonding orbitals are at higher energy, so they're less stable. That's one of the differences between the two. The other difference we're going to show you is that when we identify the space that's likely to be occupied by these orbitals, and the best example for us is a diatomic, where you have, say, I don't like these, but I got to use them because I bought them. The space between is going to have a higher probability of finding electrons in that bonding orbital between atoms. And the anti-bonding orbital is going to have a node in the middle. So it will still have the same concept of electrons occupying a space between atoms to form the bond, but they can also occupy anti-bonding orbitals. It depends on the energy level, and we'll go through some examples. And the concept here is interference. I think I'm going to let I've got a video coming up that'll help identify what we mean by interference. Interference is a concept that is particularly applied to waves. When a wave's coming along and another one's coming along and they meet, they will interfere. And so if you have a crest meeting a crest from the other wave, then it's going to be higher. It's going to be a positive interference. If you have a crest and a trough meeting, or a crest and a crest opposite one another, they'll cancel, and you'll have 0. So we still have the concept of the sigma molecular orbitals. If it's on axis between the atoms, and now I know I said in the beginning that molecular orbitals are spread over the entire molecule, but we're going to use terminology from the localized electron model in encoding the different molecular orbitals that are going to come out of the combinations. So we're still going to call sigma molecular orbitals as predominantly on axis between nuclei, and pi molecular orbitals as off axis. Right, and this just emphasizes the fact that once we've created the molecular orbitals, and they don't form until the molecule forms, right? They don't pre-exist the molecule. They only form as the molecule is created. So by some mysterious chain of events, the atomic orbitals, as the atoms approach one another and bond, then the atomic orbitals fade away and the molecular orbitals occupy the molecule.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay, so the concept here is presented as simply as possible for your first. Has anybody ever heard of that interference concept before? Now, if you haven't had physics, then you probably never saw it. This is as simple as we can make it, right? It's just, actually, it's not, well, I guess it is two-dimensional. The waves are moving this direction, and then the amplitudes are that way. But you have to expand that when you're talking about atoms and molecules, expand that into 3 dimensions. So it's kind of hard to imagine that. We have to do it mathematically. But the same things happen on a 3-dimensional scale with electrons in molecules and around atoms. I like to think of it this way. If I haven't shown you this before, when we're thinking about an atom with a nucleus, and then we have these orbitals out here, then think of the electron not as a particle, but as a wave. And it occupies this space if the wave perfectly has the right distance for a standing wave to exist. In other words, when I come around here, it needs to perfectly balance like that. Right? If it doesn't meet there, then the wave can't occupy that orbital. Right? It has to move to another orbital. So that's leading into the idea of quantization. In other words, we know electron can only be here or there, not in between. And that's part of the reason, because it has to be a standing wave in that orbital. Well, the same thing happens for molecules too. So we talked about interference. The word we left out was superposition. And that just means what happens when a wave meets. At any instant of time, one part of the wave is superposed on another part, and you either get an increase or a decrease in the combined amplitude. Okay. Now, one other thing that this video showed you was a simple pattern of interference. Both waves has exactly the same wavelength and the same amplitude as they approach one another. But in reality, what you're likely to find is one wave approaching and another wave approaching that's entirely different. But they will interfere, and they produce complex patterns of constructive and destructive interference. Now we're going to try to ease into the idea of molecular orbitals for atoms in terms of constructive and destructive interference. So for bonding orbitals, and here we have two hydrogen atoms with one electron, and on the bottom part of the slide, you're going to see the 1s orbital for one atom and the 1s orbital for the other atom, which is where the electrons are going to live if they're atomic. And then they can do one of two things. They can either constructively interfere, which gives you bonding molecular orbital, or destructively interfere, gives you the anti-bonding molecular orbital. And notice that you do have a node between the atoms. Anti means, well, obviously it means not bonding. It runs counter to the bonding orbitals. So what we're going to end up doing is saying how many electrons are in bonding orbitals that we create for the molecule, how many are in the anti-bonding orbitals, and if you have an equal amount, then you don't get a bond at all. You don't get a molecule. But if you have more bonding than you do anti-bonding, then there's a chance that you can have a molecule. That's where we're headed. So this MO1 on the bottom is at a lower energy than the orbitals of the free atoms. In other words, when we combine those two and get bonding orbitals, we get lower energy than the atomic orbitals. And the combination that gives us the anti-bonding orbital is at higher energy than the atomic orbitals from which it is derived. So this is what it would look like schematically if we're trying to represent what happens when we combine dispense with that. So if these are the atomic orbitals, and we're deriving, and this one has one electron in it, this one has one electron in it. This is one atom, this is another atom. Right? And this in the middle is going to represent the molecule. So we have energy levels here. And we find that if we combine these, we're going to get from 2 atomic orbitals, we get 2 molecular orbitals. One of the molecular orbitals is going to be at lower energy, and this is the 1s. This is the sigma 1s, excuse me. The sigma derived from the 1s orbitals. And this is going to be the sigma star derived from the 1s. And we use that star to represent antibonding. Okay? So to show how they were created, we usually do dotted lines to draw them together. All right, so now we're going to use Hund's rule, just like we did for atomic orbitals. We're going to use first is the Aufbau principle. In other words, electrons go into the next lowest orbital as we add them in. We have to go to the very lowest possible that's unoccupied and build from there. So we build from the bottom up. Okay. And Hund's rule says that we can put, if there are degenerate orbitals, which there aren't here, there's only one, so we don't have to worry about that. Then we put these 2 into this orbital, and they have to be opposite spins. So whatever it started out as doesn't matter. In the molecular orbital, this is going to be occupied by 2 electrons in opposite spin. So you'll see that this is a bonding orbital with 2 electrons, and there are no electrons in the antibonding. So that means that's good. Dihydrogen molecule is preferred. I mean, it's the molecular orbital model predicts H2 molecule. All right. I've already mentioned this. Generally speaking, the labels that we apply to the molecular orbital models say something about their shape and from where they are derived. So if this is a 1s orbital here and this is a 1s orbital here, this sigma bond is going to be formed from those 1s orbitals. Right? It can get a whole lot more complex than that, but that's why we're starting here. Really simple. All right. And sigma means that the bond is on axis between the atoms. All right. That's repetition there. So what if we go to an F2 molecule? This is a shorthand way of representing a molecular orbital sequence. And notice that we've got sigmas and we got pi's. So if we were to start over, let's give myself a little bit more room here. Let me see if I'm stealing my own thunder. No. Okay, so if this is the energy of each one, and we start off with fluorine here, then we know that we're going to start off down here with 1s orbitals, right? And then we're going to have 1s and then 2s, right, maybe about here. And then we're going to go to 2 p's. And how many p's do we have? 3. Okay. So we got 2 p's. And let me move that up some. Oops. Let's put it up here. Because that's all we're going to need for fluorine. Spread things out so we don't get bunched up. So our 2p orbitals here are x, y, and z. Oops. There we go. Okay, so how many electrons do we have here? 9. And we have 9 here. So that means we have a total of 18 electrons. Right? Okay. So now we're going to form, well, I better move this up a little bit also. Okay. So we can form 2 molecular orbitals here, sigma 1s and sigma 1s star, right? Well, let's put the electrons in first. 2, 4, 5, 6, 7, 8, 9. So those are electrons in the atomic. Now we're building the orbitals, and these 2s orbitals can also combine into sigma and sigma star from the 2s, like that. Okay. And since you can only have, now we've got these 3 p orbitals, but you can only have 1 sigma, just like the valence bond theory, only 1 sigma between on axis. So we could create 1 sigma down here from the 2p. And then we have to have a sigma star up here derived from the 2p. And as it turns out, this sigma and this sigma star are at extremes of the bonds that we're going to create from these. So within these, now we can get a pi, 2 pi's at from the 2 p's, and we can get pi stars from the 2 p's. Okay, so let's see if we conserved all our orbitals. 1, 2, 3, 4, 5, 10 orbitals, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we conserved all of them. And we've created bonding, antibonding, bonding, antibonding, bonding, antibonding, bonding, bonding, antibonding, antibonding. Okay, and derived from these. Okay, now we can put the electrons into them, working from the lowest energy up. And these energy values here, the reason I can put this one down here and this one up here is because the model, the equations, the quantum equations tell us that for this molecule, that one's this energy level, this one is that energy level, and these are in between. Right? We can, on occasions, you can take these and flip them. Okay, and I'm going to show you examples of that in a minute. But for difluorine, this is the example, and we have 18 electrons, right? So we can put 2 down here, 2 here, 2 here, 2 here, 2 here. 1, 2, 3, 4. So that's 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18. That's it. We don't need that orbital. Okay. So this is a shorthand way of writing that. And if you look at that from left to right, energies increase just like we did with electron configurations. Right? Lower for the left, increase to the right. And we get a sigma, sigma star, sigma, sigma star, sigma, pi, actually 2 pi's, and 2 sigma stars. And we didn't differentiate these 2 here at those levels. We just noted that there are 4 electrons in those orbitals because they are degenerate. They're exactly the same energy. So we wrote them like that and just put 4 electrons into them, recognizing that we could draw them out and say sigma 2p from x's and sigma 2p's from y's, for instance. No, x's would go into the sigmas. Pi's would be y and z, if you wanted to get that detailed. But barring that, those pi orbitals can hold 4 electrons because there are actually 2 orbitals in each one. All right. Your head swimming yet? It's a lot to take in. Very often what we do is we borrow from the valence bond theory, and we only write these molecular orbitals based upon valence electrons only. So we sort of simplify things. And for calculation purposes, that works just fine. So what I would normally do is just eliminate these 1s orbitals, right? This one level is core electrons. These are valence. So I'd start here and do the 2s and just leave the 1s's out. That means I'd have to recount these so that we only have 7 and 7 or 14 valence electrons to fit in to those orbitals. Now here's a calculation that we can do and do a prediction as to how strong the bond is going to be, what we expect the bond strength to be. And it's called bond order. The calculation is really simple. We just count up the number of bonding electrons, count up the number of anti-bonding electrons, and subtract them and then divide by 2. Okay, so because still 2 electrons for each bond. Okay, so we count up the bonding electrons with this model. Then we have 2, skip that one, 4, 6, 8, 10, 12, I think. And let's see, anti-bonding would be 2, 4, 6, 8. Okay, divide by 2. Let's see if that works. 4 divided by 2 is 2. I'm counted wrong. So let's try that again. Let's see, 2, 4, 6, 8, 10. Wow, that's obvious. All right. 12 and 8 is not 18. This has to be 10. There we go. So, and that's another reason that that shorthand notation is useful, because it's a lot easier to read that than it is to try to figure out in here. So, what bond order? We know about single bonds, double bonds, and triple bonds, and how a double is stronger than a single and a triple is stronger than a double. The implication here is that this bond order says that this is a single bond between these 2 fluorines. And that's what we predict with the valence bond theory also. The difference is bond order doesn't have to be a whole number. Whereas the concept of single, double, and triple bonds, they have to be whole numbers, 1, 2, or 3 bonds. But the bond order can be fractional. Okay, and I hope to show you 1 or 2 of them before we're done. Okay, So if we go back to the dihydrogen model, right, we have 2 minus 0 divided by 2 is 1. So we expect the bond between those two atoms to be a single bond. And that's what we find in the laboratory. Now, what if you make an ion out of the H2? Where is that electron going to go? In other words, to make a negative ion, you have to add an electron. You have to force an electron onto that H2 molecule. If you do that, where is it going to go? It has to go to the next antibonding orbital, right? That's the next highest level. So it has to go into the antibonding. Then if we calculate the bond order, 1 divided by 2 is a half. We have decreased the bond order and weakened the molecule. Because it used to be 1, now it's only a half. What if we take away an electron? I don't have one for that, but suppose instead of we add 1, we make it an H2 positive. And we have to take 1 away from the sigma 1s orbital. That means we still only have 1 minus 0 divided by 2 is a half. So either way, we've weakened the molecule. Now, that won't always be the case. This is just for this example. What happens if you make ions? Right? Where do the electrons go? And what does it do to the strength of the bond?
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the 2 atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these 2 atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these 2 different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed 2 new molecular orbitals from our 2 atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, 1 from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system, and they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which On average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. Now, you might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
Okay. I wanted to put these up here for oxygen and nitrogen to make a point. Actually, a couple of points. This one's going to be normal. Okay. Let's see. And we're only looking at the 2 P's. So that means 3 each for these nitrogens and 4 each for the oxygens. Okay. And when we create the molecules for the nitrogen, we get everything in bonding orbitals. So we have bond order equal to 3. And for oxygen, we have 2, 4, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. We'll talk about that sigma pi mixing in a minute. All right, for this slide, we're just saying that the easiest ones to understand to start with when you're looking at molecular orbitals for the first time are the homonuclear diatomic molecules, like the difluorine, the dihydrogen, the dinitrogen, the dioxygen. All of these that we learned from the very beginning were diatomic. Those are the easiest ones to represent. And we're not even looking at the 2 S's. For calculating the bond order, we don't need the 1 S or the 2 S in here. We get the same result with or without. Also, with the SP mixing or the sigma pi mixing, with this one is flipped. This is the way we looked at it before, but this one's flipped. The bonding orbitals are down here, so they're going to fill up the same way, and you're going to get the same bond order calculation as with or without. Okay. So this bond order is going to be equal to 2. And this gives nitrogen a triple bond. This gives oxygen a double bond. And the bond between those 2 nitrogen atoms is massively strong. It's very strong. It's virtually inert, makes the molecule inert. That's why when you buy a bag of chips, it's puffy, right? And when you break it open, you hear sort of a pop. They used to, when they made these fried foods, snacks, where the oil could possibly go rancid over time, which is exposure to oxygen, oxidizing the molecules. The fatty molecules would give it that nasty flavor and smell. They used to put antioxidants in there with them. And some products still do that. And what that does is scavenge the oxygen so it doesn't react with your oils. Well, there was some concern about the health effects of those antioxidants on when you eat them. So the industry moved toward just excluding oxygen entirely from the bag. And they do that by pumping it full of nitrogen. Nitrogen is virtually inert, so it's not going to react with your molecules. And the oils only start potentially becoming rancid after you open the bag. But they blow nitrogen in there when they seal the bag. Okay, so that's a discussion of inertness based upon the bond order. The other thing that we're going to see is, I think it's on this slide. It's the concept of paramagnetism versus diamagnetism. Paramagnetism is a property in which if you take the molecule and try to insert it into a very, very strong magnetic field, like you would find in a NMR. When you put it in there, it tends to draw it in. There's an attraction. So magnetism, para means with or alongside. So it wants to be drawn into the magnetic field. Dia means opposed to. So diamagnetic substances want to be repelled by the magnetic field. On the molecular orbital, on the electronic level, paramagnetism implies that there are unpaired electrons. In other words, you don't have a balanced spin, because if you have paired electrons, they're spinning in opposite directions and they cancel their magnetism out. Okay? But if you have unpaired electrons, one or more, then they start to add up. They're spinning in the same direction. They tend to add to their magnetism. So for nitrogen, you have all paired electrons. That means it's going to be diamagnetic. Okay? Whereas where oxygen, you have two unpaired electrons, it's going to be paramagnetic and drawn into a magnetic field. The valence bond theory cannot explain that. When you draw the Lewis dot structures, remember dinitrogen, we drew it like this, right? Which would be accurate because all the electrons are shown paired. But when you draw the oxygen, the Lewis dot structure says they're paired also. So you can't predict paramagnetism for oxygen based on the Lewis structure. Only the molecular orbital model explains why it's paramagnetic. Now this is a real phenomenon that you can see. Let's see, is it in the next slide? Now this shows a MRI, magnetic resonance imaging, is the medical application of this technique. Where NMR is nuclear magnetic resonance is the chemical equivalent. And this device simply has a balance attached to it. This is stylized. And the sample is lowered into this strong electromagnetic field. And the balance can detect either repulsion or an attraction and measure the value of paramagnetism or diamagnetism. As a demonstration, right, if I had one of these big horseshoe magnets and some liquid oxygen, I could show this to you. You just pour that liquid oxygen into that gap between the poles of the magnet, and it sits there as a liquid until it evaporates, and then, then it's gone. But that demonstrates paramagnetism. Oh, Professor Dave wants to talk. Let me see. Did I have something else I wanted to say first? No, I guess not. So take it away, Professor Dave.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n=2 shell, we can see the 2s orbitals combining in precisely the same way, and then the two p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 antibonding electrons, including the sigma 1s star antibonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
I know there's a lot of repetition in there, but for this topic, it's probably good to hear it several times and from different people. So notice that when Professor Dave was describing this phenomenon of flipping the S and the pi bonding orbitals, he referred to it as sp mixing. It's more accurately as sigma pi mixing, but you'll see it both ways. And notice the breaking, at least in the period 2, the break occurs between nitrogen and oxygen. So the dioxygen difluorine will have no significant mixing. That means that the sigma and the sigma star are at extremes, and the pi stars are in the middle. But when you go to the left, when you go through nitrogen to the left, the pi molecular orbitals are lower in energy. And so I see the sigma and the pi is flipping. This is another representation of mixing and not mixing. And it includes information about the actual electron populations of these molecular orbitals and the effect it has on their magnetism. So we find that diboron would be paramagnetic because it has unpaired electrons. And oxygen, of course, is paramagnetic, but the others are diamagnetic because all of their electrons are paired. And the bond orders are also given. The bond order for diboron is 1, so it's predicted as actually occurring. Dicarbon and dinitrogen, of course, have increasing bond orders. And you find that all of these molecular orbital predicts that all of these homonuclear diatomic molecules do exist. Okay. Now the fly in the ointment comes when we try to pair up heteronuclears. In other words, atoms that are different from one. They're going to start off at different energies of their atomic orbitals. So that's going to influence the energies of the molecular orbitals that come out of those combinations. And this is where it gets really messy. And I'm only going to show these as examples because understanding how to construct an energy diagram for a heteronuclear diatomic molecule is actually beyond me. Right? I didn't go that deep into chemistry to understand how they actually do these by hand. All right, so this is just to illustrate the fact that carbon being further to the left, the atomic orbitals are going to be higher in energy because the effective nuclear charge is lower for carbon than it is for oxygen. Right, so that we noticed that and came across that with trends in the periodic table. Right, from left to right, you get an increased electronegativity because you get more protons at the same principal quantum number. And you also get a shrinkage. So the diameter decreases also. And all of that manifests itself also in energy levels. So as you move to the right, the energy levels get, the orbitals move closer to the nucleus because the nucleus is adding protons. You get more and more nuclear charge. So that's why oxygen is lower on this side and carbon is higher on this side. So when they combine, we get, let's see, sigma. Okay, what's happening here is before we had the 2s orbitals from each one down here, and they were doing their thing, and then the 2p's up here were doing their thing. But since the energies are so different, now you get interspersed interactions between the 2s orbitals creating sigma and sigma stars intermixed with the ones that are created by the mixing of the 2p's. So it gets complicated. And this is a carbon monoxide. So we've drawn the carbon monoxide molecule using our VSEPR model, and we've determined that carbon monoxide has a triple bond. Right? It should be written like this. With the VSEPR, carbon monoxide is going to be like that. Right? So that's 2, 4, 6, 8, 10. 10 valence electrons. And let's see, Do we have 10 there? 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons there, and that agrees with our VSEPR model, our Lewis dot structure. Now, if we calculated the bond order, let me see. Are we going to do that? No. So let's go ahead and do that. So the bond order here, we calculate as, let's see, there are 2, 4, 6, 8. That's it. There are 8 bonding electrons. And how about anti-bonding? Let's see, move up here. There are 2. There are 2 anti-bonding. So that's 6 divided by 3 is 2 is 3. So it does predict a triple bond. They're saying that the CO molecule is isoelectronic with N2. That may be true, but I'm not sure that the orbital orders are the same. Possibly they are. Well, we do get the same bond order. That's for sure. Now, when we have HF combined, then now we have we don't have orbitals of the same principal quantum number overlapping, right? Hydrogen only has one s, so it has to combine with 2p orbitals from fluorine to produce the molecular orbital sequence of orbitals, right? So 1s definitely is going to be higher because there's only one proton in there with the 1s orbital. It's actually going to be higher in energy than the 2p. But when we combine them, we get a single sigma and a sigma star, and put the electrons in there, and you get a bond order of 1. So we do predict that HF is a valid molecule, and we find that in the laboratory also. But the difference in energies is what's puzzling. All right. Oh, let's look at that diagram again. Where are the electrons in the molecular orbitals? They're in the sigma orbital, and notice that the sigma orbital, molecular orbital, is closer in energy to the 2p orbital of fluorine. It's way, way far away from the energy level of the atomic orbital of hydrogen. That's another way of looking at electronegativity. When you see H and F combined, we expect the bond to be polar in that direction, and the electrons to spend more time on this side than on the hydrogen side. And if you look at the energy difference between the two, you see why that is. Because fluorine contributes an orbital that is much lower in energy, and the electrons are going to occupy the molecular orbital that is closer to the 2p than it is to the 1s. So those electrons want to spend more time around the fluorine. Even though the bond order is 1, it is polar. And that's another way to see polarity in terms of energy levels. Okay. That's what this diagram is trying to show. Oh, that's the same. I just said that. Okay. So we're going to reintroduce that concept of delocalization. The molecular orbitals, as an overall comparison between the valence bond theory and the molecular orbital theory, the molecular orbital theory is a massive delocalization of electrons as compared to the valence bond theory. And we're going to try to make sense of the tweak that the valence bond theory was required to make in terms of resonance, and how that can be explained in terms of molecular orbitals and delocalization. Okay. These pi molecular orbitals are formed by the p atomic orbitals. So there's some overlap there, sideways overlap, that gives those diagrams that we saw earlier, where you get the bonding orbitals tend to have a molecular, electronic density offset, but occupying regions that are between the atoms. This tends to delocalize those electrons, just as it would for any of the other bonds. But when we look at one specific example, this benzene, for instance, benzene, this is the way we draw it in organic chemistry. Now they've added everything into it just so that we can not make any mistakes. We typically draw a double there, and each one of these has a hydrogen on it. In organic chemistry, we don't draw the carbons and we don't draw the hydrogens. Wherever two lines meet, if there's no symbol there, that's a carbon. Okay, so we have 6 carbons here. And we don't draw the hydrogens in. They are understood. It just keeps things from getting too messy. Right. If we do need to put some other atom, like an oxygen or a nitrogen or a sulfur, then we will draw those in. Okay. So this is going to resonate based on the valence bond theory. This structure would resonate with this structure. Okay. And all we do is just shift the double bonds around one position. If we shift them again, we come back to this one. So we only have 2 structures to resonate for benzene. But benzene is extremely stable molecule. It's difficult to break those bonds, if that's indeed what you want to do. So we're gonna talk localized electron model and molecular orbital model together now. If we look at the localized electron model, we're going to get sp2 hybridized orbitals in order to bond. Maybe I better draw the hydrogens in. In order to bond, and this is one of the other fixes that's required for the localized electron model, is this concept of hybrid orbitals. Right? So we know that the benzene molecule is planar. Right? It's perfectly flat with everything, all the carbons, all the hydrogens in the same plane. And we only get that with sp2 hybridization, right? Which means trigonal planar. So we get one of these sp2s that way, one this way, and one this way to overlap the carbon next door, right? Or the hydrogens. But what does that leave us? That leaves us an unused p orbital, doesn't it? We still have an unused p orbital that is perpendicular to that plane. So what forms is what's known as a pi system. And you don't actually get double, single, double, single, double, single. we know that that doesn't happen because the bond lengths have been measured. The bond energies have been measured. And each one of these bond lengths is exactly the same. If it was a double single, this one would be longer and weaker. This would be shorter and stronger. But it doesn't happen that way. These are all identical bonds. So the explanation is to form this delocalized electron density over and under the plane of the molecule. That's what we're trying to show there. In this case, and this happens in two different types of molecules. In this case, we have an aromatic system, which is the strongest delocalized electron system when you have aromatics. But you can also get a stabilization or a decrease in overall energy for conjugated systems. And for conjugated systems, you have, say, a string of carbons, which would form this zigzag like that. And then every other bond is a double bond. Now, these are actually double single bonds. But what you have is this is sp2 hybridization, and you have these unused p orbitals, and they overlap down the length of the bond. And they delocalize the electrons that way. Now, this is best explained by molecular orbital theory. I mean, we can understand it with valence bond theory because of mental gyrations. But explaining it in terms of energy is left to the molecular orbital theory. So remember the nitrate ion, NO3 minus. It's a polyatomic ion. It has a single negative charge distributed over the entire structure. But we can draw, and we've left out lone pair electrons. We can draw these three structures that are equivalent Lewis structures. And we have to resonate them in the valence bond theory. But if we introduce the concept of delocalization, then we find that, and we measure equivalence of each of the bonds, just like we did with benzene. Each one of those bonds between nitrogen and oxygen is exactly the same length, exactly the same energy. So this is one way to represent it with that dotted line. I may have shown you that before, I don't remember. But this is what it would look like in a space-filling model where you have the electrons shown delocalized above and below the plane with those pi electrons being overlapped. Oh, before I get to that, I wanted to mention one other thing, and we might see this in a review, is we drew this diagram where we had, say, well, if we had like s orbitals and then p's, in some cases, you get molecular orbital combinations that are exactly at the same level as the atomic orbitals. Now, I don't know I can't give you an example right off the top of my head, but these, since they're at the same level as these, they're neither bonding nor anti-bonding. They're non-bonding orbitals, and non-bonding molecular orbitals are predicted by the theory, just so that you know that that's possible. And you can populate those with electrons with the Aufbau principle, right? As you move up higher levels, then it's going into those non-bondings. Now, what do you do with those when you calculate the bond order? I think you leave them out. You don't even put them in bond order calculations. Just the bonding versus the anti-bonding. Because the non-bonding electrons are going to have no impact on the calculation, on the reality of bonding versus non-bonding. Okay, the last slide is evidence. So that you don't think that we're just pulling this stuff out of are remote and dark locations. This is evidence for the molecular orbital theory and the influence and actually the reality of the energy levels for molecular orbitals. This is called photoelectron spectroscopy. We can do it for individual atoms or for molecules. It works in any circumstance. What we do is, it's kind of like my mind's gone blank. It is the photoelectric effect. That's it. Where you shine a certain frequency of light at a metal, and if it's high enough in frequency, it will eject an electron. Right? Below that, what they call the work function, it won't eject any electrons. It'll just absorb the energy and get hotter. So this photoelectric effect can be used to by firing photons of a known energy at the sample, and then the electrons that are emitted, you can measure the kinetic energy of those electrons. If you subtract their kinetic energy from the energy that was impinging on the molecule, the difference there is the energy of the electron that was ejected at those various electrons that are ejected. You can calculate their energies within the molecule, because all the energy that you're impinging on those electrons either goes into removing them from the atom, or any excess energy then is converted into kinetic energy. Right? So the total is the energy that you impinge on the sample. Then if you, and you know that energy, then if they have any kinetic energy that you measure, subtract it from that. What's left over is the energy at which the electron sat in the molecule. So we get this spectrum. And we find that it corresponds exactly with predicted energies for the molecular orbital model for each of the electrons. That's just physical evidence. And we like that. When we can experimentally confirm outcomes for a given theory, then we know we're on the right track with that theory. It's when the experimental outcomes don't agree with the theory, that's when we get into trouble, and we have to invent. I've gone through that before. You know, you have 3, possibly 4 options. Okay, I think that's the last slide.